Well, let's watch this video, which is indeed representing different methods of work holding in a vise on the turning machine. There are different methods of holding the workpiece on a lathe depending on the shape of the workpiece and also its size. The most common method of doing this is making use of three-jaw chuck, as you can see it here, and making use of a key in order to tighten the workpiece in the chuck. And if we are facing with a part that is not circular, then we can make use of four-jaw chuck, and each of the jaws can be adjusted independently. And also we have got collets that can be used for holding rotational parts. When we make use of the collets, there is less time that is needed for tightening and holding the part in place. For loading and unloading, indeed, you can easily do that. Well, and this is representation of different types of machining operations that are performed on a lathe. That is tapering, producing a conical shape on the lathe, facing, taking material from the face, as you can see it here, reaming, that is to improve the quality of the surface of the internal shapes or holes. It removes just a little bit of material and improves the surface finish significantly. And also boring is another operation doing the same thing. It removes more material than reamers. It is indeed, boring is referred to as internal turning. Parting off, when a narrow cutting tool is used in order to cut the material into pieces and separate it from the bar of the raw material. Well, now let's move on to the slides for the problems. As of this week, we are going to spend more time on the homework problems, and we are covering the example problems in the Q&A session. So let's just quickly go through the equations that are used in this session. Well, the equation sheet we have got, it has got a number of equations for different machining operations. The ones that we will be using for turning operations are listed here. There are 5 equations. First equation 21.1 is the one that relates cutting speed to the spindle speed. V stands for cutting speed. Its unit is meters per minute or millimeters per minute. It depends on the unit that is used for say representing the size of the workpiece. If D is in millimeter, then what we get for cutting speed will be millimeter per minute. If D is in meter, then what we get for V is in meters per minute. N represents the spindle speed, and its unit is RPM, revolutions per minute. Do not confuse N and V. Cutting speed V is different from spindle speed N. N, it's very obvious what it is the number of rotations of the spindle speed per minute, and V is the distance traveled on the surface of the workpiece by the tip of the cutting tool. And then we have got this equation here, which is giving us the difference between the initial diameter and also 2 times of depth of cut, which is giving us the final diameter. We've got another equation down here, which relates feed rate FR to feed F. When F is multiplied by spindle speed, it gives us feed rate. Often students confuse between these two. Please note that feed rate has got a different unit from feed. The unit for feed rate is millimeter per minute, and the unit for feed is millimeter per revolution. We've got another equation down here for computation of the machining time, TM, and that is a function of initial diameter of the workpiece times the length that is to be machined divided by multiplied by pi and divided by F times V. F stands for feed and V stands for cutting speed as it was defined before. And the last equation, RMR, material removal rate, is an equation which can give us the rate of material removal, and this is an indication of the feasibility of the say feasibility and efficiency of the machining operation. As material removal rate is higher, it means that we are doing a more effective machining operation. And it can be computed if we have the values of cutting speed, feed, and depth of cut at hand. Okay, now moving on to the first problem of the homework problems. What is it asking us to do? It is telling us that in a production turning operation, the foreman has decreed that a single pass must be completed on the cylindrical workpiece in 5 minutes. So what we are provided with is the TM right here, TM, the machining time for a straight turning operation. Workpiece dimensions are given, and those include 400 millimeters in length and also 150 in diameter. So we have got diameter and length of the workpiece at hand. The value of feed or F is also given, 0.30 millimeters per revolution, and also depth of cut is given. D represents, lowercase d represents depth of cut. So we have got D, we have got F, dimensions of the workpiece, and also TM. This is all what is given. Now we've got to see what cutting speed. Cutting speed, how do we represent cutting speed? Parameter V represents this. What cutting speed must be used to meet this machining time requirement? So we have machining time at hand. We want to see what is the cutting speed giving us this much of machining time. If we take a look at the equation sheet right here, we are after an equation sheet which gives us the value of cutting speed, and also it has other parameters that are given included in it. If we take a look at the equations, this one is the one that represents or gives us the value of machining time. However, we have it is 5 minutes. We are after this one, we are after a V. In order to compute the value of a V, we've got to have TM and other parameters that are included in this equation. Those include feed rate, feed, F, L, and D, which are the dimensions of the workpiece. And if we take a look at if we take this equation out from the equation sheet and substitute, solve it for cutting speed, then this is what we will get. Cutting speed is what we are after, TM is given, feed is given, and dimensions of the part are also given. So we can easily substitute the values and compute the unknown value of the cutting speed. So this much of cutting speed in meters per minute will give us a machining time of 5 minutes for machining this workpiece. So it was just an easy problem, taking the equation out, solving it for cutting speed, substituting the values, and also getting the result out of it. Okay, the next one is a little bit more challenging. Is there any question on this problem? No questions? Okay. Cutting speed is a very important parameter. Indeed, in the machining handbooks, always this is something that you can find. If you know the material that is used for the cutting tool, for making the cutting tool, and also you know the material of the workpiece material. These are the things that we are expected to know. Then we can get the value of cutting speed out, and if we have the value of cutting speed out, we normally compute the machining time. However, in this problem, it was given the other way. That is, machining time is given to us, so we computed the value of cutting speed. Okay, moving on to the next problem. A tapered surface, the one that is shown down here is a tapered surface, that one. So the cutting tool is moving in a direction that a conical shape is produced. A tapered surface is to be turned on an automatic lathe, some sort of CNC machine. The workpiece is 750 in length with minimum and maximum diameters of 100 and 200 millimeters respectively. So what is given to us so far is the length, which is this much, and smaller and larger diameters of the conical shape. And those include, say, these three parameters are given: length as well as smaller and larger diameter. All these three are given. The automatic controls on the lathe permit the surface speed to be maintained at a constant value of 200 meters per minute. So we've got the cutting speed, or V, which is given, and that is constant by adjusting rotational speed as a function of workpiece diameter. That is interesting. If we take a look at the equation sheet again, the first equation up here, as we can see, it relates cutting speed to, say, workpiece diameter and spindle speed. So if we know the value of cutting speed, that is 200 meters per minute, and we want to keep it constant, knowing that diameter is constantly changing in conical shapes, when we are machining the part, the diameter is changing all the time as the cutting tool is moving forward. So in order to have a constant value for V, we've got to change N continuously so that it results in the same value of V. So back to the statement of the problem, once this is moving in this direction and performing the machining operation, diameter is constantly changing. If we want to have the same value of cutting speed, that is 200 meters per minute, then what we need to do is continuously adjust the spindle speed or rotational speed. This one, we've got to continuously reduce it so that eventually we get the same value for cutting speed. This is possible only in CNC machines. In traditional machines, this isn't possible. Okay, what else is given? Feed F is given 0.25 millimeters per revolution, and depth of cut D is also given. Is this much? Depth of cut is also given. The rough geometry of the workpiece has already been formed, and this operation will be the final cut. Determine the time required to turn the taper. So what are we after? The time, machining time. This is what we're going to do, or TM. And also rotational speed. Rotational speed at the beginning and also at the end of the cut. So what we are after is TM right here for this operation, as well as rotational speed, or N. There will be N1 and N2 because in the beginning we have got something, at the end that we will have also another spindle speed. These are the ones that we want to compute. Okay, in order to do this, let's take a look at the equation sheet to see if there is an equation that is helping us. If we want to do this equation, which one of the, to compute the machining time, which one of the equations can we use from this equation sheet? This one? This one is good for computation of machining time only if we are dealing with a straight turning operation, not conical shapes and not irregular shapes. So forget about making use of this equation for computation of the machining time, because the operation is machining of a conical shape and not a straight turning operation or cylindrical part. So this is not good. If we cannot do this, then is there any other equation that can help us to compute TM? Not directly, but indirectly, one of the equations could be used in order to help us. Which one? If we take a look at this last equation, it gives us material removal rate. Cutting speed is given, the statement of the problem. F is given, D is also given. So all these three are given. If we compute material removal rate, and also if we know that how much of the material is to be removed, that is the volume of the material to be removed, can it somehow help us in order to compute the time needed for machining? Well, if we know the volume of the material to be removed, and then we have the material removal rate at hand, then we can easily divide the volume of the material to be removed by material removal rate, and that will give us the time needed for removing this much of material. So that's what we are going to do now. Well, what we do is that First, we compute material removal rate, take this equation out from the equation sheet, substitute all these three parameters that are given. Cutting speed is given. We convert it into, say, millimeter per minute. By multiplying by this factor, we do the conversion of the unit, and then we multiply it by values of F and D that are given in the statement of the problem. It gives us this much of material removal rate per minute. Now we have material removal rate computed. Next, we've got to compute the volume of the material to be removed. What is the shape? The shape is a conical shape. Well, there is an equation down here making it possible for us to compute the surface area, the area of the frustum of the cone. This equation, I have taken it out from the internet. You can just Google it. Of course, in the time of the exam, you don't have access to the Google, so you can expect this equation to be given to you. So the task of us is to compute the volume of the material. If we compute the surface area of this conical shape, knowing the thickness or the depth of cut, that is 3 millimeters, then we can easily compute the volume of the material to be removed. In order to do that, what we need to have is the radius of the smaller circle and the larger circle, as well as its height. So height is indeed equivalent to the length of the cone, and that is given up here, 750. And the smaller and larger radius, the diameters are also given. That is 100 and 200 respectively. So we divide this by 2, giving us the radius of smaller circle and larger circle. Having this at hand, we compute the value of S, which is this side, and then substituting all values in this equation, we can easily work out the surface area of this conical part, and it is this much. Now what we have is the surface area of the cone, and we have got the material removal rate. Next, we've got to multiply this surface area by 3 millimeters, which is the depth of cut, and that will give us the volume of the total material to be removed. And that's what we will do. Moving on to the next slide, we've got the depth of cut that is given. So accordingly, volume of the material is equal to area times D, area times depth of cut. So area is computed, and this is also given. We can easily work out the volume of the material to be removed. Then, if we divide this value by the material removal rate that was computed in the previous slide, then we can easily compute Tm, or material removal rate, for this problem, and that is this much. Okay, Tm is now computed. How did we do it? We didn't make use of the equation on the equation sheet because this is not a cylindrical shape. That equation on the equation sheet is only good for cylindrical shapes. For this one, which is a conical shape or any other irregular shapes, we've got to take the same approach, and that is to compute the volume of the material to be removed and divide it by material removal rate. It gives us time. For part B of the problem, to compute spindle speed for the smaller diameter and larger diameter, what we need to do is to make use of the first equation on the equation sheet. It is this one up here. We've got to make use of this equation up here. If we have the value of cutting speed and diameter, then we can easily compute the value of unknown parameter, and that is spindle speed. So we do it this way. We take the equation out, solve the equation for spindle speed, substitute the smaller diameter first, and cutting speed is given. We compute the value of spindle speed for the smaller diameter, and similarly, when you substitute the larger diameter, you get the value of spindle speed for the larger diameter, giving us the same cutting speed of 200 meters per minute. Please note that now we have multiplied this by 1000 in order to convert the unit of cutting speed from 200 meters per minute to 200,000 millimeters per minute. So this conversion of the unit is also needed. Okay, is there any question on this problem? No questions? Then let's move on to the Next problem. Okay. Next problem here. Well, we know that the chalk is used in order to hold the workpiece in place. However, this is only effective if the length of the workpiece is short. For longer workpieces, like the one that is in here, that is in here, that is in here, we've got to make use of a center in order to support the other end or the free end. If this is not in place, what will happen? If we just have the long workpiece, massive workpiece, a bulky workpiece which is in here, its mass is high, its length is high. If we want to make it rotate and machine it, then how do we do it? It's not possible if it is not supported on the other end. And you know the reason. Because of, say, gravity, which is pulling it down, this one will not stay in place properly, so we will not be able to machine it. So a center is used in order to hold it in place. Now let's see what this problem is asking us to do. A 10 centimeter diameter workpiece that is, so the diameter of the workpiece is given, D is given, and that is this much, is 62.5 centimeter long. So L is also given, D is given, L is also given. Is to be turned down to a diameter of this much. So DF is given. That was initial D that was given, D0, and this one is also DF. So we want to turn it down to this diameter 8.75 using two passes, not in one pass, in two passes. When the depth of cut is high, we normally don't machine the part to that given diameter in one pass. It's not possible because it is applying too much of say force on the machine and also on the cutting tool, so it may damage the cutting tool or the machine itself. For this given scenario or this given problem, two passes are considered in order to perform the machine task. Cutting speed is given, which is this much. Feed is also given. So we have got the cutting speed, which is V, and that is 90 meters per minute. Feed or F is also given. And depth of cut is given. D is also given. Okay, so if we take this depth of cut, double of this will be reduced from the workpiece material, because from two, this is rotational part, and these depths of cut will be reduced from both sides of the diameter. So if this is the depth of cut, 2 times of this will be reduced from the workpiece material after one pass. After two passes, 4 times of this value will be taken out from the material. So what is left is the say the final diameter. The bar will be held in the chalk and supported on the opposite end in a large center. This is what I just explained, and it is shown down here, of course, in the picture. The center here is supporting it. With this work holding setup, one end must be turned to diameter, then the bar must be reversed to turn the other end. So what we do, we take two passes from this end, okay, and then we reverse it. That is, this end will be going inside of the chalk, and the other end that was already in the chalk will be machined. So it has to be done in 2 different steps. Using an overhead crane, the time required for loading and unloading is this much. So 5 minutes time is needed for loading and unloading of the workpiece on the machine. And 3 minutes time is needed for reversing. So we've got 5 minutes time for loading and unloading, plus another 3 minutes for reversing the part. This is already in place. And we've got also 4 machining operations, 2 passes on one end, and then after reversing, 2 passes on the remaining, or the other end, or the remaining length of the workpiece. The task of us is to compute the total time required for machining this part. It is also mentioned that we've got to consider an allowance of 1.25 centimeter for machining of each pass. Reason, we normally cannot machine the part exactly to the required length. We've got to get started a little before the workpiece. We've got to start cutting, and it has to go inside of the material on the other end. So in the beginning and in the end, we've got to consider a little bit of extra travel of the cutting tool, and that is equal to 1.25. In order to do this problem, to compute machining time, of course, we can make use of the equation on the equation sheet because this is straight turning. And in order to do that, what we can do is to take a look at the equation sheet right here, get this equation out from the equation sheet, and do the computation. Because this is a straight turning, this equation can be properly used to do that. And it has to be used 4 times because there will be 2 passes on each end, and there will be 4 passes altogether. We've got to substitute the values of each pass in this equation, get 4 values of machining time, and then add them together, plus loading and unloading time, and plus reversing time. There will be 6 different time components that are to be considered. So it is fair to make use of this equation for each pass, but I am going to do it in a different way. And that is, let's get back to the statement of the problem. And that is to actually do it this way. How are we going to do that? First, we are going to cut more than the half of the length in one pass. The total length is given up here, that is this much, 62.5. We normally machine more than half the length in the first end, and that let it be 37.5. It doesn't have to be this exact length. It has to be something more than the half of the length. Say, for example, this much. So in the first pass, we machine this length of the part, and of course, we've got to add this allowance to it later on. If we want to machine it for this length, we've got to compute spindle speed. If we have the value of V at hand, that is cutting speed, and that was already given, and this 100 is used in order to convert the unit from meters per minute to centimeters per minute, because all the other dimensions are given in centimeters. So we multiply it by 100. Now what we get is cutting speed in centimeters per minute divided by 10, which is the diameter of the workpiece in centimeter, times pi. What does it give? It gives us the required spindle speed for machining this part. And then feed rate. If we have a spindle speed, we can compute feed rate because we have feed at hand, and we know F times N, or feed times spindle speed, gives us feed rate. Now we have computed feed rate, FR. If we know the length of the part to be machined, and that is this much, we are machining this length, 37.5, plus allowance of 125. This is the length to be machined. If we divide it by feed rate, what it gives us is the required machining time. So this is another way of doing the same thing. So 2 different ways of computing TM. First, make use of the equation on the equation sheet. It will give you exactly the same value as we have got here. Or compute the length, the total length to be machined, divided by feed rate. And that's what we do for the first pass. So the required time for the first pass from the first end is this much. This reduces diameter to this much, 2 times of the depth of cut. Depth of cut is given up here. 2 times of this, take it out from 10, it gives you this diameter. Now we have only taken one pass. We've got to take another pass from this end in order to bring it down to the desired diameter. What is the desired diameter? What is up here? It has not yet reached to this diameter. So we redo this computation on this same end, and this is how to do it. Because now starting diameter is down to this much, we've got to redo computation of spindle speed, and it gives us a lower value than a higher value than what it was before, because now the diameter is smaller. It gives us a higher spindle speed in order to get the same cutting speed. And then similarly, we compute the feed rate. Now we have got a different value for N. However, feed is still the same. So it gives us the new value for feed rate. Now we have a new value for feed rate. So dividing the total length that was 37.5 plus 1.25 comes to this much, divided by new feed rate. It gives you the new value for machining time, and that is the time needed for machining of the, say, for machining of the, say, second pass on the same end. Now, this end is reduced, the diameter of this end is reduced to what we want. We are done with the first end. Now we've got to reverse it. We reverse it and we similarly compute the machining time for the other end. Okay, again, the diameter is 10 for the other end. So we substitute 10 in place and compute the spindle speed for it, and then compute the feed rate, and then the remaining length of the workpiece is the difference between 62.5, that is the total length of the workpiece, minus 37.5 that is already machined, this much, plus the allowance. Dividing it by the feed rate that is just computed gives us the third machining time, that is the first pass on the other end. And similarly, we compute the second pass, the time needed for second pass on the other end, which brings it down. The second end is down now to 8.75. So what happened now is that we have got, say, we have got all the lengths that is machined to these lengths. Now we have got 4 TMs plus 2 other times. For loading and unloading, we've got to consider 5 minutes, and then 5 minutes for loading and unloading, TM1, TM2, 3 minutes for reversing. These are non-machining times in these two components. 3 minutes for reversing, and again, the second end, first pass and second pass. We add all these figures to one another in order to get the total value of machining time, or total cycle time, that is 19 minutes and 19 minutes point 72. Okay, that's the way of computation of the cycle time for machining of this part. Is there any question on this problem? What I'm asking you to do is do this problem at home and make use of the equation that we have on the equation sheet for all these 4 passes, and then you should get the same value. If you did, then you did it right. I have done it, and I'm sure you will get the same value if you do it correctly. If you didn't get the same value, so something is wrong, and figure out what went wrong with it. Okay, any questions on this? No questions? Well, as of next week, we will be doing the lab activities. So I'm asking you to spend some time on the problems, and there is a lot of information on the Blackboard side. So go through all the information on the Blackboard side for the lab activities, read the task sheets, and prepare yourself for the lab. Go to the lab quite prepared with everything if you are doing the unit on campus. Go to the lab prepared. If you go to the lab unprepared, then the lab staff will not allow you to get started with the activities. So to avoid any disappointment, please go through all the information that is provided to you on the Blackboard site. Okay, that's all for this Tute session. The rest of the problems that is on milling and drilling will be covered in the next week's Tute session. If you have got no questions, I'm going to conclude this session. And thank you very much for your participation. Okay, thank you so much, and you are welcome.